Okay, kids, Charlie Busso here, page 11 in the bonding notes. And here we go. We have to draw the Lewis dot diagram for calcium oxide. Calcium, of course, is a metal, and calcium has a 2882 electron configuration. Oxygen, the nonmetal, has a 26. The calcium is going to lose these 2 electrons and send them over there. So in order to show calcium with a 2880 electron configuration, we're going to have calcium in an empty box, an empty bracket, and the oxygen, which has 6 valence electrons, which I'm going to draw, 6 valence electrons. It's going to get the 2 electrons that came out and goes now into oxygen to make oxide. And we'll put this in brackets, and it has a -2 charge. Calcium oxide. The only kind of bond here is ionic. Now, it is a little tricky on purpose because there's a transfer of 2 electrons. You might be tempted to say double, but it's not a double bond. Ionic bonds are just positives attracted to negatives. The positive cation attracted to the negative anion. Doesn't matter how many electrons transfer. It doesn't matter that it's positive to negative to. It matters that it's positive negative. This is only an ionic bond. An alloy is a mixture, usually 2 metals, but sometimes it can be a metal and a nonmetal. Now, when you melt 2 metals together and you let them chill, literally chill back into a solid, you have a mixture of 2 metals. Sometimes you can do that with a metal and a nonmetal. When you chill them back together, they have slightly different physical properties that might actually be better. Examples: sterling silver. If the queen comes to eat and you want to give her the best silverware, it's not all silver. Silver is beautiful, but it's soft. You can't really cut steaks with silver. So sterling silver is silver and copper melted together. Now, it's mostly silver. You don't even see the copper, but it's in there for extra strength. There's also stuff called brass. Brass is equal to zinc and copper. And depends on how much zinc or copper you put in there, it gives it different strengths. But a brass musical instrument is way more durable and way less tarnishy, and it's just got a lot of better qualities. It's not a new compound, it's a mixture. And if you take a tuba and you melt it, well, if you know the melting points of zinc and copper, you can heat it up to the melting point of 1 and melt half of it and then get your metals back. The last one I'm going to talk about is called cast iron because my brother is a plumber. This is iron and carbon, and when you melt this iron and you powder it with the carbon and you stir it all up, when it gets chilled and solid again, the iron is remarkably strong, but it's very, very much not malleable. If you hit it, it will crack, but it also doesn't rust. And we used to make the toilet pipes in the house out of this stuff because a lot of times, or all the time, they're wet and water's going through them. They never leak. They never rust. They're very, very heavy, though. And now we use plastic because it's a lot less physically demanding. And plastic doesn't leak either. So cast iron, brass, and sterling silver are all examples of alloys. Now, I have to show you a model. I don't know how this is going to work. I'm going to pick this camera up. This is a physical model, if I get further away, of sodium chloride. Now, the gray and the green, I'm going to say that the green wooden balls are going to be chlorine and the gray ones are going to be sodium. And in sodium chloride, you have sodium, chlorine, sodium, chlorine, sodium, chlorine, and it works in 3 dimensions as well. Going in 3 dimensions, they alternate back and forth. Now, when you have a compound like sodium chloride that alternates back and forth and back and forth, the coordination number, it's called. The coordination number for sodium is 6. That's because when you have an Na, there's a chlorine above, to the left, to the right, below, to the back, and to the front. Each sodium ion is surrounded by 6 chlorides. Now, the coordination number for chlorine, well, when you have chlorine, above it there's a sodium, and below it there's a sodium, and to the left and right there's a sodium, and to the back there's a sodium, and to the front there's a sodium. So each chloride is also surrounded by 6. And the coordination number is 6. And now, when this particular coordination ratio, it's surrounded, they both are 6. They make a very, very boxy compound. Look at this, the shape of this. See how 90 degrees it is? I know this is a little dizzy making me very dizzy. Very 90-degree angles. This next one coming in, this is called calcium chloride. Calcium chloride's kind of boxy. I'm really struggling with this, but it's definitely kind of funky too. Look at that shape. Look at that shape. The reason this crystal has a different shape is because there's a different coordination number. The big idea about coordination number is, depending upon what it is, the crystal shape takes form. When your coordination number is 6 and 6 over here, you get a nice, very boxy compound like sodium chloride. The crystals, when you look at a crystal of sodium chloride with a magnifying glass, it looks very boxy. And when the crystals are big enough to see with your eyes, they're still very boxy, because at the ion level, they're boxy. And with this other calcium carbonate, it's got a much more bent and angular kind of a shape. It's kind of cool looking, but it is not boxy. Now, in the notes, you're going to see there's something called uric acid. And when the crystals get bigger, they look a little bit like double-pointed spears. Now, some people have a disease that's called gout. I used to get gout, but now I'm taking medicine. Gout is when the uric acid in your body is not excreted fast enough. Now, usually uric acid breaks down, it gets into your bladder, through your kidneys, and you urinate out what's called urine. And it's called urine because it's got uric acid in it. Now, if you dissolve the uric acid crystals in water, they dissolve like salt dissolves, regular table salt. It gets invisible and it just exits your body. But with gout, the uric acid doesn't leave your blood. The kidneys and not able to get the uric acid out fast enough, and the uric acid backs up and it turns to crystals. And there'll be one little crystal, very small, but it'll look in this sort of a shape. And it usually ends up in your big toe, because you walk around all day and it falls to the bottom of your body due to gravity. And then overnight, more and more uric acid ions crystallize onto it, and the crystals get bigger and bigger, and you end up with a fairly good-sized crystal like this in your big toe, and you can get a really painful condition in your foot called gout. Runs in families. My grandmother had it, my father had it, my cousins get it, I get it. My friend Carl gets it too, but he's not related to me. Usually you get it in your foot. Sometimes you get it in different places. My grandmother used to get it in her arms. Once I had it in my knee. It stinks, but depends upon what's called the coordination number. And for us, it's really just a vocabulary word. The coordination number is the number of ions of one kind that surround the ions of the other. The number of positive ions that would surround an anion, or the number of anions that surround a cation. And the combination of the two coordination numbers at the ionic level will form the shape of the crystal, and then it just gets bigger and bigger and bigger until it's physically big enough to see with your eyes. So that's just a vocabulary word. All right, the last thing on this slide is about carbon monoxide, which makes a really weird bond. Carbon's going to look like this, and oxygen's going to look like this. This needs 4 electrons. This needs 2 electrons. And mathematically, it doesn't really make any sense. So here we go. We're going to draw the carbon double bonded to the oxygen. But this doesn't work because the oxygen gets 8 electrons, which is a full octet, and this gets 6, which is not going to work. The only way to make this work is to do this. The carbon is going to double bond to oxygen, but the 2 electrons that used to be up on top are going to get thrown into the middle. So we have here a double polar covalent bond on the bottom of this diagram, and we have something called the coordinate covalent bond, which means that the oxygen just lends 2 electrons in. So in some ways it looks like a triple bond, but it's not triple. These 2 pairs of electrons, there's 2 pairs that are shared. That's the double bond. Then there's something called coordinate covalent bond. And the way we're going to show that is going to look like this. It's going to look like a double bond, and I throw a little wiggly line in there to say it's not a triple bond, but something else is going on, and that something else is called a coordinate covalent bond.